Hi, I'm Koustav Das and I'm going to give a presentation on the topic of distributed ML using federated learning. Uh, so I will talk about the basics of federated learning and the basic concepts used, and my group mate Debraj will talk about the project itself, the libraries used, the test data used, and how we implemented it. So first up is how it all started, the inception of federated learning. Uh, this quote is taken from a blog written by Google Research, and as it shows at 2000 in 2017, federated learning Google started to implement federated learning. So, what the question is why? Why did the news? Why did they need federated learning in the first place? So, centralized machine learning applications had two major problems. First one is the problem of privacy, the leaking of user data, that is, and another huge problem was latency. Huge amount of data, user data, needed to be passed among the clients and the servers, basically the server, centralized server, and that causes network bandwidth problem and latency problems. So they started to implement and come up with the came up with the they came up with the concept and started to implement federated learning. So is a quick an overview of how distributed ML using federated learning is implemented. The first thing is there is a centralized server, but the model is decentralized. Basically, the copies of the model that are stored in the centralized server ML application is sent over to the user devices, and the users train on the user data is used in training inside those devices, and only the training data is sent back to the central server, not the user data. So the privacy, as she says in the comic, the privacy nightmare is solved, and uh, there are no individual updates sent to the cloud. So latency problem somewhat is solved in this case. They first started using it in Gboard, which uses recommendation based on your past type history, and they didn't want to leak the user typed uh, keywords and data to the third party. So the next step is uh, how does it work. The next strip is taken from the Google's federated learning website itself, so credit goes to them. As I said, there is no the ML application itself is decentralized. That is, there is a local copy present in each device, uh, in each user device, and the users train their device. The model trains on their device itself and sends all the training data. And the question is, if the application itself runs on the user device, will it not consume resources in the user device? When someone is using a smartphone, they don't want it to run another third party application like a federated learning application. So as we can see in the next slide, that only the devices that are available, that is, there are some criteria for choosing which devices are available for using the training model. uh, they are, as it is shown here, they're charging, they're idle, and the internet connection is on. So there's a pool of devices. The ML application will select a pool of devices available. Then it will select a subset of that from that pool. How the criteria will be set by the centralized algorithm. It will see if the data present in the user devices are relevant to the algorithm, to the training model being used. So here some user is chosen and some users are taken out of the subset. Next, as I said, that a copy of the application which is of a few megs, as it is shown here, that very small size, it is sent over the internet to the user device, and it takes some time to train on the device itself, and the training data is sent back to the model. the centralized model. Now another question arises that can we not reconstruct the user data using the training data? So we'll talk about that in the last couple of slides, I guess, in one slide. So next we'll go with once the training is over, we need to test the model. So testing is done basically in the same way. The centralized server sends back the training data back randomly to user devices. Some user devices are used for training purposes, and some user devices are used for testing purposes, and the accuracy result is sent back to the server. By using that accuracy result and checking that accuracy result, the server updates its model, and as it's written, it is done privately, securely, and with federation. That is, uh, every user device has its say when it wants to share its data or not. Mostly not. Now that question again comes that if we use if we, when we are sending the training data itself, can it not be the case that uh, the training data, the user data is reconstructed from the training data itself? So the answer is Google is using another algorithm, that is secure aggregation algorithm. So secure aggregation algorithm is basically the training data is encrypted first in the user device, sent over the wire or the internet to the central server. The central server uh, puts back those training data into a whole model without decrypting it. Once the model is built up, the whole model is built up, it starts to decrypting it. So it never has the key that the user has. So if it doesn't know the training data itself, it cannot decrypt the individual training data. It can never know about the user data. You can never construct the user data. There are other problems which are more complex. I haven't included in the slides. And last of all, uh, why do we need to use federated learning? Why centralized? Sorry, where why do we need to use centralized federated learning? The massive uses are in healthcare and self-driving cars. So healthcare is, there are chances of data leak, high chances of data leak in healthcare systems. That is, patients will send their health data or monitoring data over to the servers present, uh, which is running the ML application itself. So that is a big privacy mistake. So hospitals can use federated learning in this case, in which case the application is distributed, as I said, to user devices that are monitoring the patients, and come up with a training model that can be updated in the central server. Another is self-driving cars. Self-driving cars basically need to mimic the human behavior of driving. So again, we need real-world data from humans, and that's why and there are problems with latency and privacy again. So we can use federated learning in this case too. So next, Devraj will talk about what kind of test data are used, and how we have implemented, which libraries we have used, and I'll give it over to you.
Hi everyone, this is Debraj and I'll be talking about our project. So, if we go, so I'll be mainly walking you through our abstract, how to set up the project, what is our code about, and what is our output. Also, some of the references and links will be given below. You can check them out if you want to run the project in your local system. So, for our abstract, we are going to do this project or do this federated learning on the image dataset, and for the model that we are going to use is distributed multi-layer perceptron, and we are going to create 10 virtual clients which will be acting as our different systems, you can say. For the dataset, you can find that in Kaggle. So we have taken this dataset, which is open source dataset. It contains 0 to 9 uh, levels for the images, and total training dataset is like 42,000 images, as you can see. So basically what we will be doing is we will be doing our project on this dataset itself, and the link of the dataset is given in the setup portion when you are going to look into it. Now, before starting, our main primary libraries that we are going to use is TensorFlow, Keras, and CV2 also, just to read the images and everything. So apart from that, as we are doing it on Google Colab, there is no need to install the libraries specifically. But if you are doing it in your local system, then you might need to install them using a pip command, or you can just check them out on how to install them. Suppose TensorFlow, like if I type it out, TensorFlow installation. So you will be able to see, like if you are using some Anaconda, maybe Anaconda IDE, then you can like get how to install TensorFlow there also. So basically for each environment you need to set it up individually, and this shouldn't create any issue. Let me check one thing. Okay, so let me open the project file quickly. So this is our project file. As you can see, we are doing it in the Google Colab, and so these are all the libraries that we have imported. And let me quickly go through the PPT here once. Yeah. So now we are in the code walkthrough portion, and I'll be walking you through our code, which is basically the generating the output which we are trying to predict using distributed MLP. And okay, so as you can see here, we are just importing the libraries in this first 7 segments. So basically, let me just run this code as well, just for you to see if the results are coming fine or not. Okay. So as you can see, this green mark here confirms that this is running properly, and yeah. So I have left this portion out just to show you guys how we are doing or how we are getting the dataset. So basically, what we have done is after downloading the dataset from here, we will be getting a zip file, and that zip file we are uploading it into our Google Drive. From there, what we can do is import that Google Drive into the Google Colab and get that data from there itself. So here, if I type this command out, or if I run this segment out, then it will ask me to connect to my Google Drive, and yeah, I will give the permissions as necessary. The permissions have been given. Let's wait for a while. It will show you the green mark. Okay, as you can see, this has been mounted at contents as drive. So what we can do is we can check it. Yeah, see, it just came right now. So what we can do is we can go there and go to my drive here, and you will see that in my drive there is this folder called federated.zip. So this is basically this folder here that I have uploaded in my Google Drive, and this folder contains all the dataset. Okay, so what we are doing is we are using this command to unzip the file, and once we are done unzipping the file, the data is there. You can see if I run this thing out now. Let me quickly run it. It's still unzipping. You can see the images there. Total 40,000 images are there, so it might take a while, but let's see. As you can see, this is getting unzipped and everything. Okay, this is done. Now once this is done, if I refresh it here, you will see that in my drive there will be a folder. Wait, let me quickly go somewhere else to refresh it. Yeah, you can see the folders are here now. All the files that I have unzipped are now here: test sample, test set, training sample, training set. And so what I am going to do is now load the data from the training set and test it out, test our model out on the test set. But before that, we need to create some functions or methods to define how to load those data, how to scale those data, and everything. So if we go back to our presentation PPT, you can see here. Okay. Okay. Now let me go here. So this function definition, as you can see, this load function here or the load method here, what is it doing? It's basically it is going to load the image dataset, and once it is done loading, it will give us info that it is processed. And what is it is going to return to us is basically the image data and image levels to us. So for each client, we are going to load the data. Okay. So this is a function that we will be calling later on. Done. Now I have defined the image path here, which is the training set. So we'll be using the training set here to load our model. And image paths are basically all the where the image contains actually, nothing else. And we are creating a image list and label list separately with verbose of 10,000. This is a label binarizer that we have taken earlier from the imports. Now basically, and also we are going to train split the data from using train test split, and on a 90:10 ratio on the training data set. So let me just quickly run it. Yep, you can see that we are using the load function here, which will give us the image list and the labels, and for each image and for each labels we have loaded the data. Now this is a function where we are defining how many clients will be there, and we will be passing the data here, which is the image list and also the label list, and we'll define the number of clients, and each client will have an initial name of clients. It will be something like client 1, client 2, client 3, like that. So this function is doing what? So we are doing basically, for suppose if I am giving 10 clients here, so there is a list here which is containing dictionary of list of dictionaries basically, and each dictionary will contain the name of the clients, so and their data. So the client names will be like the initial name, which is clients, comma clients basically underscore 1. I is basically from 0 it is running, but in this scenario we will be keeping it as the 0th client will be named as client 1, like that, and the 9th client will be named as client 10, like that. And for the data part, what we are doing is we are basically taking the data and shuffling them up, and dividing the data into equal parts and putting them in the client. And after this create client function is basically returning us the dictionary of clients and their respective data, and this data contains a tuple of the image data and level. So let me quickly execute this method. Done. Now as you can see in this portion, we are creating the clients where we are calling this function that we have created earlier, and we are defining the number of clients as 10. And so if you are running this function, done. Now you can see that if I run the client here, you can see let me quickly run this function. It will return us a dictionary of client names and their respective data. So it's going to take a while. It's just for your visualization purposes, nothing else. But if the data size is large, we might choose to skip this step or just check the first value of the clients. Let's wait for a while. It will execute just in a while. As long as it executes, let me just go to the next steps here that we have taken. So for now we are in this part where we have created 10 virtual worker clients and we have distributed them equally. Okay. Now what we will do is, as the dataset size is huge, let us quickly stop it because it is going to take some time. Okay. So now for each, suppose 40,000 data is there, and if we split it among 10, so around you can guess around 400 images on each client will be there. So what we'll be doing is we'll be processing those 400 images in a batch of 32. So this is basically the batch size. So what we are going to do is take those data and make them process in a batch, so that it will be easier for us to train and also take lesser time. And 32 is just a random number. You can choose it to any number, but we have chosen 32 as our batch size. And here we are using TensorFlow slices to create those 32 slices. Okay, now let me quickly define that function that is defined. Now what we are going to do is create a dictionary which is going to take each clients and create a batched data version of them. Okay, so basically this client batched dictionary is going to store our batched data. So we are calling the function here. As you can see, for each client I am calling the batch data function and passing the data into that. And this data contains the whole data. Suppose 400 images are there, and we will be processing them in a batch of 32. And after that is done, so what we are going to do is we are creating a test batch which is getting just the x test and y test that we have previously defined, and also batching them up. Now we are defining our simple multi-layer perceptron model. So what this model does is basically we have just created a simple method, and that is basically we have created, as you can see, 1 2 3 layers, and each layer containing 200 neurons. And for the activation functions we have used ReLU for the hidden layers, and for the last output layer we have used softmax as our activation function. If you want to read about the ReLU and softmax activation functions, you can just type it up in Google, and yeah, you will see what this activation function does. Basically, activation function is something which will help us to activate a particular neuron or rather perceptron here in this case, because neuron is in terms of human biology, and in deep neural networks, or we can term them as perceptron. So for each perceptron to get activated, it needs an activation function, and that activation function depends on weights and biases. For the properties, we are using an learning rate of 0.01, and 100 communication rounds will be there. For the loss function, we will be using categorical cross entropy, and for the matrices, we are going to test our model performance using accuracy only. For the optimizer, we are using stochastic gradient descent, and this is how our optimizer is going to be. These are the parameters that we will be passing in our model. Now, these methods that we have defined here is basically all the methods where we will be scaling the weights for the neural network, and also from each so this method is basically weight scaling factor. This method is doing what? This method is basically our scaling our weights to a normalized weight. Next is scale model weights. Then each model, from each client we are getting a model, and for each model we are going to normalize that also. So this is that function for us. And then we have some scaled weights. Basically, when all the clients are giving us their individual models and their respective weights, then for the global model we'll be basically taking the average of all those models. So this function is basically doing that. And for the test model method, what it is basically we will be passing the test dataset, and it will give us the output. So this is basically all the 4 methods that we have defined. Now we'll be calling them. So how we'll be calling them? So first we'll be taking one creating, or rather initializing our perceptron model. After that we have taken a global build also, and for each communication round, which is 100 times, we'll be iterating through it. For each communications round, what we'll be doing is we'll be initializing the global weights, setting them up, and shuffling those client names randomly, and we'll take the data randomly. Now for each client, what we'll be doing, we'll be creating a local model for them, and that local model will also build, then compile the model with the loss function, the optimizer that we have previously defined, and also the metrics will be set to accuracy, as I have already told. And also this global weights, it's there, we have already initialized those values. These values will be changing with our gradient descent function. So what we are doing is we are fitting the data, then we are getting the scaled weights of them, and also after getting the scaled weights, what we are doing is we are basically creating a weight list where we'll be adding that particular models or particular clients weight to that. After getting that, what we'll be doing that, we'll be having all the client wait list here in this variable, and from here we'll be calling our previously defined method of averaging all the weights for the clients and storing it in average weights. Then we are going to set the global model weight according to this average weights. Then what we are going to do is we'll be testing the output with our test batch dataset which we have previously done. So let us quickly run this segment and you will see that the model will be trained. So that is all for the portion. uh, yeah, as you can see, like, it's running. It is going to take a little bit of time because there are 100 communication rounds, and for each communication round there will be a lot of steps going on there. And as this is an image dataset, it will take some time. So basically, what we have done, as you can already guess, we are creating, to sum it up, basically we are creating 10 virtual clients. We are giving them a multi-layer perceptron model. They are training on their own respective datasets of in a batch size of 32, and after that we are getting all those aggregated results and averaging them up. Then we are setting our weights from those models, and those weights will be taken as our input in our global model, because we are getting those weights from all those models, so we are selecting the best average one, and from that global model we are going to test with our test dataset, and that will produce us a better result compared to the normal conventional methods. Let me come back in a while, uh, as long as it finishes. Okay, so basically this process took quite a while. It has been around 10 or 15 minutes, and so yeah, basically the training is the testing has been done with 100 communications round. As you can see, these are the communication rounds, and it started with 0, as you can see here, with an global accuracy of 88% and a global loss of 1.66 percentage. So after refining it through all those processes and all those weights, we have achieved an accuracy of 97.310%, which is a lot better compared to individually running on each clients. And this sums up our project. As for the references, you can see we have taken the references of these blogs and this analyticsvidya.com, what is that, how to do the federated learning things. And as for our project link, it is shared openly. You can just go to this link and check out our project if you want. And that's for the part. Thank you.